Hi, my name is Theo Garcia, and today I'm going to be talking with you about seismic monitoring of rainfall-induced subsurface changes using Jensen Shannon divergence. So the objective of the talk is to be able to describe soil moisture using seismic data. The importance of being able to measure soil moisture is because this is a very good indicator on how the forest is doing and its fertility, and it is a very good way of making plant diagnosis. Also, they be able to detect it using seismic data is especially useful because seismic data is capable of getting data from nearby, from the soil on a bigger area. So it is an average of a lot more space, which could be a better indicator of the general soil moisture of the area. It is also theoretically you can specify different depth, the different depth that you want, so you can see at different depthness how the soil moisture is. Whereas if you wanted to do this using more conventional ways, you have to dig and put a different sensor at different depthness. So it is generally could be more convenient using geophysics data and seismic data. So the index, this is how the talk is going to be. First, I'm going to give a little bit more of a background, then a proposal, result, and then conclusions. So talking about background of the data acquisition was in Martillo Forest, which is about a 30-minute drive from campus. We went and we dig three holes and we put different sensors. We put the same sensor, sorry, at these three spots. You can see on the image the spots where we put it. We put two of them very close by, around 20-meter space, and we put a third one more far apart. So I'm going to be referring as the close pair. And if we grab one of those in the close pair and the farther apart one, I'm going to be mentioning it as a far away pair. So I'm just gonna point that out that I'm on the right. I did personally do the holes. Um, so talking about the methodology itself, the way that a seismic data works is that it is a multiplication of both the signal itself and how the Earth responds to the signal. So the soil moisture information, which is what we're interested in, is inside the Earth response. So if we are able to measure the Earth response at different times, for example, of a rain event, and we see how it changes through this event, we can therefore see how if we can there see the soil moisture information, and we could perhaps describe it and compare it with the real moisture information. So the way that it's going to be working is we're going to be using statistics and a monitoring methodology. So how this works is we put the three sensors in a specific range, and since we want to single out the signal effect in the seismic data, we average all of the data that we have, and since the signals are going to be coming from all directions, if we consider all the data, the signal effect should average itself out if we do it properly using statistics, using enough data, using it comparing it in all directions. So this is the way that we're getting rid of the signal effect on the seismic data, and we're just gonna be left with the Earth response. And this is also a really good way to keep track of the long-term effects. Since we're doing monitoring, we can then therefore, since we're going to be doing it for a long time, we can see various seasons and see the effect of the temperature and all of these seasons, and how does this also correlate with moisture. So the way that we're going to be the metric that we're going to be using is the Jensen Shannon divergence. So since we're going to be having three Earth responses per station, and if we take these three Earth responses as if they were a probability distribution, we can use these divergences. And the equations are here on my right, on my left. So it just quickly explain it briefly. The F and the J are both distributions probability. And basically the Jensen Shannon is just a numerical value of how similar a pair of probability distributions are to each other. The closest to zero, the more similar they are. It's just that here it is at the JSD, just for a quick reference. So the methodology itself is going to be, we grab the close by pair and we get at the Jensen-Shannon divergence of those two Earth responses. So from two Earth responses, we get a single numerical value. And then when we grab one of the stations in the close by pair and the farthest station, we do the same. We have also a number of the J as divergence of those two. And if we compare these two numbers that we have, we get a single one. If we do the subtraction, we get a single one. And that number describes us basically how different the Earth response are in those three stations. And we get a single number. So if we do this per 5 minutes of data per station per time, like 5 minutes in a whole 3 months data, we get then a plot. We then get to see a plot, a time series plot of how the three stations behave during the whole time, which is so this is a result of only one day. So if we see, for example, the orange plot that we see is for a clear day, and the purple one is for a rainy day, which the rain starts with the red background. So we see when the rain starts on the rainy day, the KL starts to go up. Difference the Jensen Shannon difference, sorry, starts to go up and then seems to go back to how it was doing previously, and we don't see this behavior on a clear day. So we just as a reference point, we do see how the rain does seem to have an effect on the differences on these Earth responses, which is a good indicator that our metric could work. So also the plot on the right is just a quick, it's important because we divided the data through different frequency ranges, and we see that in the lower frequency ranges, the change in rain seems to be bigger and seems to be more impactful than in the higher frequency ones. We see the higher frequencies, the effect tends to mingle. So we're going to be focusing on this small frequency range. We're going to be mainly working with around 5 hertz to 50 hertz, which is still pretty high in relationship with the whole geophysics area. So this is the result uh, during the entire time. We see how at each frequency, how the divergence uh, are during the entire time series. So the red areas in the plot are different rain events. So we can clearly see that when it rains, how the values, especially in the 25 to 5 frequency band, it tends to go higher because the blue it's a very low number and the red is a very high number. How it tends to get higher, and there's a peak. There seems to be a peak at every rain event. So the specific metric that we're going to be using is we're going to be averaging out different frequency ranges inside this plot. So for example, this is the average of the entire 50 frequency band. And we see more clearly now how, first of all, it appears to have a daily pattern, and also how this pattern is very much changed when there's a rain event. We see, for example, here, how it has a specific behavior, and then when it starts raining, there's a peak that we were talking about. This tends to be in all the rain events. So if we average this out and we see the tendency of the KL during the entire time, and we compare it now with real soil moisture data, which is the metric that we're going to be working with for real moisture data, is the soil metric potential at 20-meter depth. So in the data acquisition site that we were working with, we also put real soil moisture sensors just to be able to now visually and compare it to the ground truth. And we see that the tendency of the KL metric does tend to follow that of the soil moisture data. For example, here in this belly on the red, we also see a belly on the blue. So this is a pretty good indicator that our metric is working and it is being able to describe uh, the soil moisture. It is important to mention that the frequency that we work with is a 20 to 50 frequency band for the KL. for the Jensen Shannon difference, the divergence, sorry. And now taking a lower frequency range, instead of 20 to 50, now 50 to 20, and comparing it with a more deep, uh, I didn't change it, sorry, it's 60 centimeters for both. So comparing it now to a 60 centimeter soil moisture depthness, we see how it also is able to describe it. We even see how the pattern, daily pattern that I mentioned previously, is also seen in the real soil moisture data. So this is all to say that, yes, in fact, we are able to describe soil moisture data using seismic data, and how with a single sensor, or well, a pair of them, we are able to see different depthness that we would have to dig very deep in order to get using more conventional methodologies. And also, the green plot behind in both of the graphs is rain. It is also important to mention that in neither case, there seems to be a direct impact on the red plots on the real soil moisture, which was a little bit unexpected. So this is why we also decided to check at this individual rain events and to check for relaxation times. So what we did is we took an average before the rain, and we calculated how much time it took for the Jensen Shannon divergence to return to the previous data before the rain, to see how much time it took after the rain to return to that threshold, and compare that with different intensities of rain. And we would expect a linear relationship, right? The longer the rain, the more intense the rain was, the longer it takes for the KL to return to its original values. And if we do that, we do see that in fact we do have a linear relationship with intensity of rain. It's important to mention that the purple plots are those for rains where thunder was applied. So take those with a little bit of a grain of salt, because the signal to noise ratio does have a big impact on, first of all, the KL, and second of all, the way that we calculated the intensity of the rain. So we're mainly focusing on the black points, how in both cases, at both depthness and at both frequency ranges, it does seem to line up with what we expected, this being a linear relationship. Also important to mention that in the lower frequency range, which is inherently a deeper subsurface, because a lower frequency range means a longer period, which means more the data goes through more subsurface. So on a deeper subsurface level, the slope is way bigger, which means that which is that the relaxation times are way bigger for a for a deeper level, which also makes sense because the more deep the ground is, the more time it takes for for the moisture to get out of the soil. So the general conclusions, we are able to describe soil moisture data using Jensen-Shannon divergence of long-term and also impact, like a real short-term impact of the rain. And also that the presence of thunders does worsen the signal to noise ratio. So it is a limitation of this methodology that thunder does seem to have a direct impact. Thank you.